Scalar product in component form. Welcome, everyone. Let's begin our session on the scalar product in component form. Now, in our previous lessons, we explored the geometric definition of the scalar product. As you'll recall, that method relies on knowing the magnitudes of two vectors and the specific angle between them. While that is a very useful way to understand the concept, in practice, vectors are more frequently expressed in terms of their components along the coordinate axes, using x, y, and z. Therefore, in this tutorial, we are going to learn how to calculate the scalar product more efficiently when vectors are given in this algebraic form, rather than relying on angles. This will set the foundation for the calculations we'll perform later in the lesson. Understanding the concept. Now that we've recalled the geometric definition from our previous slide, let's look at how we actually write these vectors down in practice. Instead of just looking at lengths and angles, we can represent a vector in three-dimensional space as a sum of its individual components. To do this, we use what we call standard unit vectors, I hat, j hat, and k hat. These are simply vectors with a magnitude of 1 that point along the x, y, and z axes respectively. To make our upcoming calculations clear, let's consider two specific vectors, vector A and vector B. We can write vector A as a 1 times I hat, plus a 2 times j hat, plus a 3 times k hat. Similarly, for vector B, we have b1 times I hat, plus b2 times j hat, plus b3 times k hat. In this notation, the values a1, a2, a3, and b1, b2, b3 are what we call the scalar components of our vectors. Keeping this algebraic form in mind is crucial, because in the next slide, we are going to see how to use these components to calculate the scalar product directly. Calculating scalar product. To find the scalar product of vector A dot vector B, we are going to apply the distributive law. If you remember from your algebra lessons, this is the same principle used when multiplying out two binomials, like FOIL. Let's write out the full expression. We start with vector A, which is a 1 hat I plus a 2 hat j plus a 3 hat k, and we dot this with vector B, which is b1 hat I plus b2 hat j plus b3 hat k. Now, to see how the formula is derived, we need to expand this expression. This involves multiplying every component of the first vector by every component of the second vector. First, we take the I component of vector A and distribute it, giving us a 1b1.i.i plus a 1b2.i.j plus a 1b3.i.k. Next, we do the same with the j component of vector A, which gives us a 2b1.j.i plus a 2b2.j.j plus a 2b3.j.k. Finally, we distribute the k component, resulting in a 3b1.k.i plus a 3b2.k.j plus a 3b3.k.k. Now that we have defined our two vectors, vector A and vector B, using their individual components, let's look at how we actually perform the multiplication. It looks like a very long expression now, but don't worry. In the next slide, we will see how the properties of these unit vectors allow us to simplify this entire mess into a very simple, elegant formula. Properties of unit vectors. Now, you might be looking at that long, expanded expression from the previous slide and thinking, this looks like a lot of tedious multiplication. Well, here is the good news. We can simplify that entire mess by using the fundamental properties of unit vectors. Take a look at the first set of equations. When we take the dot product of a unit vector with itself, for example, I dot I or j dot j or k dot k, the result is simply 1. This is because the magnitude of each of these vectors is 1, and the angle between them is 0, and the cosine of 0 is 1. However, look at the second set. When we take the dot product of two different unit vectors, like I dot j or j dot k or k dot I, the result is 0. This happens because these vectors are perpendicular or orthogonal to each other, and the cosine of 90 degrees is 0. Because of this, all those extra terms in our expansion from the last slide that involve different unit vectors simply vanish. They all become 0. This leaves us with a much cleaner resulting expression. We are left only with the products of the matching components. A 1b1 times 1 plus a 2b2 times 1 plus a 3b3 times 1. As you can see, the ones don't even change the values, which brings us directly to the simple, final formula we are about to reveal on the next slide. The final formula. Now that we have applied the distributive law and simplified all those terms involving different unit vectors, we can arrive at our final, elegant formula. As you can see on the screen, the dot product of vector A and vector B is simply equal to a 1 times B, 1 plus a 2 times B2 plus a 3 times B3. To put this in much simpler terms, you don't need to worry about the complex expansion we just saw. All you need to do is take the corresponding components from each vector, multiply them together, and then find the sum of those products. It is a very straightforward process. In the next slide, I will break this down into a clear, step-by-step checklist that you can use every single time you encounter a problem like this. Step-by-step calculation process. Now that we have derived the formula and seen how the unit vectors cancel each other out, let's consolidate this into a clear, repeatable strategy. If you are ever faced with a problem involving vectors in component form, you can follow this simple 3-step process to ensure accuracy. First, identify the components. Before you start any calculations, clearly list out the x, y, and z components for both of your vectors. It helps to write them down side by side so you don't lose track of which number belongs to which axis. Second, multiply the corresponding components. This means you take the x component of vector A and multiply it by the x component of vector B, then do the same for the y components, and finally, the z components. You are essentially pairing them up by their respective axes. Finally, sum the results. Take those 3 individual products you just calculated and add them all together. This final addition will give you a single, real number, which is your scalar value. As we will see in the next slide, this exact process is what we use to solve real-world physics problems, such as calculating the work done by a force. Real-world example, work done by a force. Now that we have mastered the algebraic formula for the scalar product, let's see how this concept is applied in a real-world context. In the world of physics, we often use the dot product to calculate something called work done. By definition, work done is the scalar product of a force vector, which we'll call F, and a displacement vector, which we'll call D. To make this concrete, let's look at a specific scenario. Imagine a constant force, vector F, acting on a particle. This force is given in component form as 3I plus 4J minus 2K, measured in newtons. At the same time, this force causes the particle to move or undergo a displacement, represented by vector D, which is 2I minus 1J plus 5K, measured in meters. Our task now is to use the multiplication and summation steps we just learned to calculate the total work done during this displacement. Let's move to the next slide to walk through the solution step by step. Step-by-step solution. Now that we have the scenario set up, let's walk through the solution step by step to see how we apply the formula we just learned. First, let's move to step 1. Identify the components. Looking back at our force and displacement vectors from the previous slide, we need to pull out the individual values for each axis. For our force vector, F, the x component, F sub 1 is 3, the y component, F sub 2 is 4, and the z component, F sub 3 is negative 2. Similarly, for our displacement vector, D, we have the x component, D sub 1 as 2, the y component, D sub 2 as negative 1, and the z component, D sub 3 as 5. Next, we move to step 2, multiply the corresponding components. This is where we pair them up. We multiply the x components together, 3 times 2, which gives us 6. Then, we multiply the y components, 4 times negative 1, which results in negative 4. Finally, we multiply the z components, negative 2 times 5, which gives us negative 10. Finally, we reach step 3, sum the results. To find the total work done, we take our dot product of f and d, which is the sum of those three products we just calculated. That gives us 6 plus -4 plus -10. When we simplify that, 6 minus 4 minus 10, we arrive at our final answer. The work done is -8. As we move to the next slide, keep a close eye on those negative signs, as they are a very common place to make mistakes in these types of calculations. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula we just derived, it is very easy to make small errors that can lead to the wrong answer. Let's look at 4 specific mistakes to avoid. First, be careful not to confuse the dot product with the cross product. I have seen many students attempt to use the determinant method, which we use for finding the cross product, when they are actually calculating a scalar product. Always remind yourself, the scalar product results in a single number or a scalar and never a vector. Second, watch out for sign errors. This is perhaps the most common mistake in all of algebra. When you are multiplying components, be extremely careful with negative signs. For instance, if you are multiplying a component of -2 by a component of -3, remember that the result must be +6. A single missed minus sign will change your entire final sum. Third, do not accidentally add the components instead of multiplying them. As we saw in our step-by-step calculation on the previous slide, you must multiply the corresponding x components, then the y components, and then the z components first. Do not add a 1 and b1 and then try to multiply that sum. You must multiply first, and only then sum the results together. Finally, keep an eye on your unit vector pairings. As we discussed during the expansion of the distributive law, anytime you multiply different unit vectors, such as I dot j, the result is 0. Only the products of identical unit vectors, like I dot I, contribute to your final sum. If you accidentally include terms where the unit vectors don't match, your calculation will be incorrect. Keep these points in mind, and you will find the process much more reliable as we move into our final summary. Key takeaways. First, remember that the scalar product in component form provides us with a powerful algebraic method to calculate the dot product. As we discussed in our very first slide, while the geometric definition requires us to know the angle theta, this component method allows us to find the result directly using only the coordinates, even if the angle is unknown. Next, let's restate the core formula we derived through the distributive law. If we have vector A, which is a 1i plus a 2j plus a 3k, and vector B, which is b1i plus b2j plus b3k, then the dot product of A and B is simply a 1 times b1 plus a 2 times b2 plus a 3 times b3. It is essentially just the sum of the products of the corresponding components. A very important point to keep in mind, and something I highlighted in our common mistakes slide, is that the result of a scalar product is always a scalar, which is just a real number. It is never a vector. You won't see any I, j, or k components left in your final answer. Finally, I want to leave you with a very useful application of this formula. This method is incredibly efficient for checking if two vectors are perpendicular or orthogonal. If you perform the calculation and the sum of the products equals 0, then you can be certain that vector A is perpendicular to vector B. Alright, we have reached the end of our tutorial, so let's wrap everything up by reviewing the key takeaways from today's lesson. I hope this tutorial has clarified how to work with the scalar product in component form. Keep practicing, and I will see you in the next lesson.